Okay, everything so far is looking good. The there we go. The equation you have looks fine. Your constraint looks fine. So then you took your constraint, solved it for one variable. Then you took that and substituted it in to the each z of the original equation. Looked great. You simplified. Looked great. Only thing I guess I'd say is it would be nice to have your function notation out here, so it'd still be of x, y, and z. Because it originally had equal signs. But anyway, I know you weren't doing this with the intent of me looking at it. So you did your simplification. That's all perfect. Your partial derivatives look perfect. So you said, what's the partial derivative of the function s with respect to x? So it left us with y minus 9 over x squared. Same thing here, partial derivative of y s with respect to y. That gave us x minus 81 over y squared. And then that's all your variables now. So the next step, before we move on to the second derivatives you have down here, the next step of the process is take your partial derivatives and set them equal to 0. Okay? Why are we setting them to equal to 0? Well, we're trying to find maxes or mins. And the thing you know about any graph, if it has a max or a min, at its max or at its min, the tangent line has a slope of 0. So our derivatives should be equal to 0. So anyway, so it looks like that's what you did. You took this equation, set equal to 0, and solved it. And then that's where just a little itty-bitty mistake happened. So if this was equal to 0, I would add the 9 over x squared to the other side, which brings me to this, essentially, except it shouldn't be x. This should be y. And then same thing over here. You take this equation, set it equal to 0. So when you add the 81y over y squared over to the other side, this is an x. So that would bring you to here, but except that should be an x. Okay, so now we've got, let me scoot this over and we'll rewrite this. So we've got y equals 9 over x squared, and we have x equals 81 over y squared. So we have a system of equations. Two variables, sub one into the other. So everywhere I have a y, I'm going to take that and sub it in. And I'm going to replace it with the 9 over x squared. So that's going to leave me with x equals 81 over 9 over x squared. Okay, that just came from subbing in for that y. So now that we've got that part, simplification once again. 81 over 9 squared is 81 over x squared would make x to the 4th. And then simplifying this fraction, the 81s would divide, the x to the 4th comes up to the top. So that means I've got x equals x to the 4th. So I need to solve this. Now, don't fall for the trap of dividing by x. You can never divide by a variable. We have to, what we have to do is subtract the x over from one side. So now it's equal to 0. So we have 0 equals x to the 4th minus x. So now when we're solving this, we have to result to the f word. We have to go back to factoring. That's how we get all of our answers. So when I factor this, we're going to end up taking an x out of each of these terms, leaving me with x times x cubed minus 1. So now there's going to be two solutions to this system, because the zero product property says if this is equal to 0, then the whole side's equal to 0. So I know one of my answers is x equals 0. Then for the other one, I take this, set it equal to 0, and I could use the fact that this is a difference of cubes and factor this whole thing out. But the good news that we should remember about difference of cubes, there's one real answer, two imaginaries. I don't care about the imaginaries, so I get the answer to this just by solving very easily. So it gives me x cubed equals 1, so the cubed root. And I don't need plus or minus with cubed roots. So that just leaves me with x equals 1. So I have two x values that will give me some kind of extrema, max or min. So now we're going to take these and sub them back into the previous equations. So here we go. Go right to here, our last equation that where we had x equals. So because we just solved, right here, there we go, the other equation, because we just solved for x. So now when I sub in here for x, I can get out my y. I could have done it here, it's just more work. So I'm going to sub in here. I'm going to sub in the values we just found, x equaling 0 and x equaling 1. So here's the fun part. If I substitute in 0, that would give me y equals 9 divided by 0 squared, and immediately we should be saying, nope, not going to be an answer, because that's undefined. So then we go to the other one, which would give me y equals 9 divided by 1 squared, which means simply y equals 9. So there is my x value, there is my y value. Now I have an x value of 1, a y value of 9. Now we have to go back and find out what z was. So we go back to find our constraint equation. Ooh, it's getting messy. Okay, so we're going to go back to our constraint equation and say, all right, I know y was 9, x was 1. So therefore, z is equal to 1 divided by 1 times 9. So therefore, z equals 1/9. So we can go back and make our list now. Now we know z is equal to 1/9. So we're ready. We have our answer, sort of. We have x equaling 1, y equaling 9, and z equaling 1/9. Okay, so now we've got x, y, and z. So we can take all of those and sub them back into our original equation that has s out here. So that s will result in whatever our max or min is. So we just take all those and sub them in, and that'll give us our s, whatever that happens to be. Okay, now the next question is this thing a max or a min, or what is it? And because this is section 15.4, the good news, we don't have to worry about second derivatives. We're done with those. If the problem's asking you to find a max or a min, the theory is essentially saying, because we're finding the intersection of two lines, we know that the max or min will always occur at the critical point will always occur at the intersection. We only had one of those, so therefore we know that must be the solution. So no other work is needed. There's your answer, other than you have to still solve for s. Let me know if you need any more.